Hello everyone, today we're going to be solving the following question. It looks pretty simple, not much going on. We just have a force here and we of course have the weights here. So it looks pretty simple. However, it's not as simple as it looks because most of the moments questions we've done, and we'll be doing at A level, they just have a rod. They have a uniform rod. So this rod doesn't have a width, so we don't have to take that into consideration. However, this is an obelisk with a defined width. So that's really, really important here. That's crucial. That's what adds the complexity to this question. So let's label the forces here. We have mg here, and we would have theta here, and then we'd be having sorry, we'd have here theta. Okay, this is pretty simple. So most of the time you would just say, oh, let's resolve the forces and get, so we'll do mg sine theta is equal to f cos theta. I haven't labeled f, sorry. That's what you would think of doing. However, you cannot do that because, how I said before, we have this width here. You can't treat this as a rod. This is not a rod. To treat it as a rod, you'd have to have a distance like this. That would be your rod. However, this is a different angle. It's a completely different angle. It's a different length. It's a different everything. You can't treat it as a rod, and we don't have the information to treat it as a rod. So what we do instead is that instead of getting the forces, like changing the to get the components of the forces that are perpendicular to the distance over here, what we do is that we make the distance perpendicular to the force. So what does that mean? So if we extend this force, we know that the perpendicular distance would be this right here, this distance, this dotted line over here, which I'm gonna call x over 2. You'll see why later. And for the horizontal force for the F, it'd be the same thing. It'd be we have this, so the vertical, so the vertical this well, vertical is the vertical distance. However, I meant the perpendicular distance would be the y component, the vertical distance. So this y and x is what we're gonna have to find. So to do that, that's pretty simple. We just have to do angle work. This geometry again. Let's get rid of this. Okay, let's label our mg again. Okay, nice. Okay, so what we have to do is that see this here, this is a vertical line. This angle is theta. If you're wondering why it's theta, you have alternate angles here. Right, straight line, and then we have two vertical lines. So it's alternate angles. So now that this is theta. So then to get the y component, we just have to do cos. So we have L, okay, we have y equals to L cos theta plus, we have here, that this distance is d, we have d sine theta. For the x component, it's basically the same thing. We have the x here, it's going to be this distance here, this distance right here. So that's going to be L sine theta. We have minus d cos theta. Wondering why this is minus is because this distance here is going this way. That's the distance. However, here is going that way. So it's in the opposite direction. I've chosen the left to be positive and the right to be negative. So that's why it's d cos minus d cos theta. Okay, so now we have our two lengths. Why did I say before this distance here is x over 2? It's because x would be the full distance to here, but it's not. It's only halfway through. Mg, because this is uniform, mg is exactly in the middle. So it's going to be x over 2. This exact distance, like this exact distance we had before this, is x over 2 and y over 2. Those are the components of this. Okay. So doing that, we have the perpendicular distances and we have the perpendicular, we have the perpendicular distances to the forces. That's all we need. We have mg x over 2 is equal to F y. Pretty simple. Then we rearrange for f. F is equal to mg over 2 x over y. And then we just sub in. We sub in y, we sub in x. We have x is equal to mg, sorry, mg over 2 brackets over x, which is L cos theta plus d. No, we have to do x, sorry. I was doing y. Sin theta minus d cos theta. Then we have y, which is L cos theta plus d sin theta. Okay, so to simplify this expression, we're going to divide. Let me make it nice and big. Mg over 2, mg over 2. We're going to make it nice and big because this is our final solution. We're going to divide by d cos theta. We have L over d tan theta minus 1. Then we have L over d plus tan theta. And this is our final. This is the value of f we would need to maintain this in equilibrium without any other external forces, and to actually have, to have an equilibrium. If we increase the force by a slight bit, we'll have a pulling force. So how can we test this? Let's test this. If we had that theta is equal to 0, you could see that this is going to be 0. We'll cancel this out, cancel that out. That's just going to be minus 1 over L over D. So you can mg over G. You can see that this is a negative, and you're wondering, why do we have a negative? Because when we have the obelisk like this, we just calculated the mg. And how I said, this doesn't act as a rod. The rod would be like this. So you can clearly see that the mg does actually pull this way and create a moment. The only reason why in reality, we would not need an F force pulling it this way, is because there's a reaction force here. This reaction force balances the system and maintains an equilibrium. However, in this equation, we assume that the F force, the pulling force, the tension, and the mg, the weights, are the only forces acting on it. So if there was no reaction force, if we just wanted to maintain it there with zero reaction force, we would need an F force acting this way instead of that way. This is why it's negative. So this just shows that our equation really does work. So yes, this is our final solution. This right here, right there. I hope you enjoyed the question, and see you next time.